A specialized form of refraction is called a mirage. Although the speed of light in air is only 0.03% less than in a vacuum, there are situations where atmospheric radiation is quite noticeable. On hot days, there's a very thin layer in contact with the ground, especially on asphalt where it's black. It's very hot air. Since the hot air allows light to travel faster than the cold air, what you end up seeing is bending of light rays. And so what you see as a mirage, or what looks like water, is really the sky reflecting internally off the road surface above. We're going to talk about total internal reflection, which is defined as when the angle of incidence is greater than 60%, no light passes into the glass, and each ray is totally reflected back into the water. The term total internal reflection describes this phenomenon well. So when nothing gets through and it's reflected back, it's called total internal reflection. Fiber optics and binoculars both rely on total internal reflection. It's more complete than reflection from a mirror. When light travels from high refractive index to low refractive index, so that's what N is, remember, refracted rays bend away from the normal or 90% perpendicular line. Eventually, at some critical angle of incidence, the refracted rays travel along the boundary between the two media, but they don't go through. So we get total internal reflection. Prisms are used as a reflecting surface for binoculars. So here we have light going into a prism. You have total internal refraction here. It bounces off this side and then it goes out. Total internal refraction bounces in, goes out. Binoculars rely on total internal reflection. There are two ways that we have to transport information. One is copper wire. It's bulky, it's expensive, and it's affected by interference. It can't carry as much information as fiber optics. Fiber optics uses light through thin glass tubes. It carries 100 times more information than copper. It conserves energy, so there's less signal degradation. It's not a fire hazard. It's light and flexible, and although it is a costly installation, it's cheaper material. Used for internet, phone, and cable. Smaller fiber optic cable on the right has over 6 times the message carrying capability. So here's the fiber optic, then the copper. The fiber optic cable contains 6 to 12 fibers. Each pair carries 8,000 simultaneous messages. If you look closely at a single fiber optic cable, optical fiber, you will see it has the following parts. It has a core, which is a thin glass center where the light travels. It has cladding, which helps reflect light back into the core, and it has a buffer coating that protects the fiber from damage. Hundreds or thousands of optical fibers are arranged in bundles in optical cables. The bundles are protected by the cable's outer covering called the jacket. Suppose you want to shine a flashlight beam along a straight hallway. Just point the beam down the hallway. The light travels in straight lines, no problem. What if the hallway had a bend in it? You could place a mirror at the bend to reflect the light beam around the corner. What if that hallway is very winding with multiple pins? You might line the wall with mirrors and angle the beam so that it bounces off from side to side all the way along the hallway. This is what happens in a fiber optic cable. The light in a fiber optic cable travels through the core or the hallway by constantly bouncing off the cladding or the mirror-lined walls. This principle is called total internal reflection. Because the cladding does not absorb any light from the core, the light wave can travel great distances. So here's an example, a schematic of that. Diffraction is the bending of a wave as it passes an obstacle. Diffraction occurs to all electromagnetic radiation, not just light. This idea is applied to telescopes. We want to use telescopes that have a large opening, so it allows as much starlight as possible to observe fine details and collect as much information to mitigate the effects of diffraction. Polarization is a way to force your electromagnetic light waves to go in one direction. Maxwell predicted that the EF, or electrical field, oscillates in one plane, and the MF, or magnetic field, oscillates in a separate direction, perpendicular. This occurs for any electromagnetic radiation, including light. If the components of electromagnetic wave vibrate on only one plane, the wave is said to be polarized. So here you have vertical and horizontal. The vertical filter only allows a vertical output. Horizontal filter only allows horizontal output. If you combine the two horizontal and vertical filters, you get no output because you're eliminating both directions of vibration. Polarization is confining a wave to vibrate only in one direction, either horizontally or vertically. We can use filters to block light not traveling in the orientation that we want. So polarized sunglasses will only allow light in from one direction. You can use a pair of polarized filters that are capable of blocking all light, depending on whether it is to block horizontal or vertical vibration. The remaining electromagnetic spectrum. Microwaves use high-energy radio waves. The source are high-frequency vibrations of electrons within specialized electric circuits. Microwaves are used for heating food by causing water molecules to rotate and change electric fields. They're used in radio detection and radar. So things like GPS and satellites used to transmit in TV information. Also, they can be hazardous to human health due to the high water content. If you're exposed to a lot of microwaves, you can develop cataracts. Infrared radiation is emitted from a hot substance, so it's the feeling of heat from a campfire. Mosquitoes can see IR, humans can't. We use it in things like motion detectors, heat seekers, remote controls, and other wireless devices. A false color image is produced when infrared photons are transmitted into an electrical energy and then made into an image using computer technology. Ultraviolet light, the source of that are hot objects, so hotter than visible light. Bees can see ultraviolet, used to test for metal stress in aircraft. Most ultraviolet is absorbed by the Earth's ozone layer. However, if you have excess UV exposure, it can cause abnormally fast-growing cells, which we call cancer. Melanoma is the most common form of cancer caused by UV light. UV is ionizing and can kill bacteria by breaking down DNA. It can also cause the aging of skin cells. X-rays, the source is produced by fast-moving electrons striking a metal target. Black holes give off X-rays naturally. They can penetrate body tissue, so we can use them to see bones. The darker parts of the X-ray mean that more X-rays are passing through the tissue. Because the X-rays have high energy, they have dangerous ionizing effects. Children are more sensitive to X-rays because their cells are still dividing. Gamma rays have the highest energy electromagnetic radiation. The source is radioactive nuclei or material. It is also emitted from stars. It can be used to sterilize food in a process called irradiation. It disrupts the magnetic process of bacteria cells, which cause the rotting of fruits and vegetables. It's a controversial process. You could also use it in medical imaging and diagnostic techniques. Instead of using CT and MRI, you can use it to track cerebral or brain blood flow and neurotransmitter receptors. Another example of electromagnetic radiation in your everyday life are the northern lights.